plug that in, and actually a goal seeking function which we used here, and based on the flow for a 10-year, which started jumping around on you, which is these calculations here. I just use the greatest flow that we get for a 10-year storm. We're able to size it and spit out the normal depth of the swale for a 10-year storm. The normal depth is about 0.38 feet. But one thing you'll notice is that when the water's coming here, there's quite a few driveways. So to continue the swale, we put a culvert in there. And to fit the culverts, well, first of all, the manual references that all storm drain conduit should be 12 inches. So we made the swale a lot deeper than 0.38 feet to get these culverts in, so we could kind of keep the low impact construction, so we kind of just like auger around the driveway and slide it in. So these swales here, which is kind of a cross-section of it, this is actually, it drops down about half a foot, and then from here to here is about another foot with a 1-to-1 slope. So with a 12-inch culvert, you know, it'll fit in that slope pretty well. And as you can see, 12 inches really pretty much grossly oversized for the amount of water we got here. So I mean, I did, you know, there is a known graph in the manual to determine whether a culvert's good or not. I don't have it on me, but taking word for it, it's good. It'll be, but you can tell by just because of the gross size of the pipe, it's, you know, pretty intuitive. But okay, so where were we? So one thing about these overflow structures is what we're calling them. The top of this inlet is actually above, maybe about half a foot above the bioswale. So let's just say this long bioswale, this is at the top of the inlet. And we did that because we want to encourage abstraction within this swale. So we're trying to extract as much water as we can. And when it reaches a certain level, it's going to go in the inlet and exhaust out this creek. So as it was mentioned by the Duck Creek Stormwater Group, CSOs are a problem. And the idea is, I mean, on this street, in typical Madisonville, stormwater goes right into the sewer main, and that leads to combined sewer overflows. So our thinking here with this kind of standalone structure is they were taking water on the street, put it in the overflow, or we're taking water on the street, goes to the overflow structures in this creek bed, so thus we're taking stress off the sewer system. Just to give you an example, it's actually like I believe it's like a 75-inch sewer main right here. It's like really huge, and like this whole community eventually dumps into the sewer main, stormwater and all. So, I mean, obviously this whole area is not going to have a big impact on it, but if you keep applying this to other areas in Madisonville, you know, you can take a lot of water out of that sewer main. So, on here, the manual says that you want to size your storm drain pipe according to a 10-year storm, which is what we did, and it's available here. We got the intensity equation also from the manual, and I used the time of concentration used by the FFA method because didn't really reference that spec for finding the time of concentration, but based on that and the rearranging of the mains equation, we were able to size these pipes. I did check the hydraulic grade line, and basically what I tell you is if the water is, you know, if the system's adequate, whether, you know, your water system can back up and flow out the inlet. And again, I just want to note real quick that the pipe size, the computed diameter of the pipe is like 0.21 feet, 0.31 feet, blah, 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 but we use the foot for each one because, well, one reason we do that is it's reference that, and we want to use RCP piping because, you know, it's structural enough to go under a road. You don't want to use PVC, it'll just crumble over. But, or you have to backfill with concrete, but that ends up turning to high impact construction. So, we use this large piping, and just to satisfy, again, intuitively, it looks like there's not going to be a problem. The water's not going to back up, but I did check it anyway. And so what we did was, we started with the hydraulic rating at the outlet, and based on the flow of that outlet, they actually tell you to check for a 25-year storm. Based on that flow, you can calculate friction slope, and your head loss in that pipe is the friction slope times the length of the pipe. And actually from this known graph, which you guys don't have, apologize, we get a head loss of 0.0312 feet and 0.1548 for this pipe and this pipe, which is nothing. So, I mean, the hydraulic gradient, actually, I mean, determine if it comes out, you add the hydraulic gradient elevation here plus the head loss, and those numbers are way below the inlet elevation, so it won't back out. Also, am I missing any? Okay, with the permeable pavement here, again, this is not a capacity thing. We're just doing this to kind of correct this stuff. I mean, it's just deteriorating, so we don't consider it a retention deal. Also, like for instance, this storm drain inlet, that gets paved over. We actually want to take the storm drain system offline for this road. And down here is, okay, one thing you're probably wondering, I'm sure you are, is we're adding water to a creek bed. And your Corps of Engineers, give it to me, this is all that.
The Cincinnati code, it's not the Army Corps of Engineers, it requires if you're creating an infrastructure to add to a creek, that you don't add more than 2 years worth of water for a 10-year event. So our design was based on that standard. Real quickly, I have a couple details for the sticklers in them. I didn't mean to look at you. This overflow structure to ensure that the road pipe, that wasn't a decision, that's based on the code. And also, I don't know if it's called out here, but we have a geotext out here, the interface between the bioswale and the permeable pavement.
We kind of use the permeable
to keep the permeable pavement from getting clogged up. And the permeable pavement that we have in our design is concrete pavers, which is actually implemented on Orlando, which is just perpendicular to the street. And I would say successfully in my estimation. Thank you.
So that add 2 years to a 10-year storm, we were able to do that. We were able to get the extraction we needed from the bioswales and adding these rain gardens and such. So actually, if you look on this sheet here, it gives you your retention for a 10 and a 2-year storm. And basically, if you see that 7,000 there, and you subtract that 4,000, that's what we add to the creek. And we were able to extract that successfully. And here is basically the impact of our design. This is the 2 10-year and 100-year storm. And this is the extractions for a 10-year event. Actually, you can explain that.
Okay, so after we implemented all these BMCs along Stewart Avenue, this is kind of the end result of what we were able to accomplish. For a 2-year rate event, it's about 38,000 gallons of water. For a 10-year event, it's about 62,000, and for 100 years, it's 107. And using these BMPs, this is part of the water that we capture in that year. So with the rain barrels, we're able to capture about 1,200 gallons of water. With the bioswale, we captured 9,700 gallons, and the rain garden, it was around 14,000 gallons. So if you take that away from the beginning, we had originally, it turned a 2-year rain event into 13,000 gallons of water, a 10-year into 37,000 gallons, and 100-year into 82,000. So as you can see, the 10-year rain event was taken back to the 2-year originally. And so in the end, the proposed stormwater infrastructure sequestered approximately 25,000 gallons of water, and that has the effect of reducing the impact of the 10-year event down to the 2-year rainfall event. And to put this onto perspective, you can think of like a 17-foot U-Haul truck. The volume of it is about 900 cubic feet, which is approximately 6,400 gallons. And so since we captured 25,000, that's about 4 U-Haul trucks put together. So that's the amount of water that we're able to capture.
Are we running on time, or I can collapse? I think we'll get to other issues if we have any questions. So everyone has spoken on it? Yes.